Ever notice how certain character classes in multiplayer video games can clear a map way faster than others? If you pick a tank class, you have a massive hitbox and heavy armor. The extra weight forces you to lumber at a crawl. But if you pick a lightweight ninja class, you can sprint, dash, and scatter across that exact same map in a fraction of the time. And if the developers trigger a server-wide speed boost event, suddenly every player, big or small, gets an energy spike that lets them cross the map at maximum speed. This exact logic is how smells, gases, and molecules naturally spread through our world every single day. In the physical world, things naturally want to move away from highly crowded areas and spread out into empty spaces. Imagine someone standing in the corner of your living room and spraying a bottle of perfume. At first, all those scent particles are densely packed together right near the bottle, but slowly they travel outward, bumping into the air until someone sitting on the opposite side of the room can smell it. Scientists have a specific name for this exact process: diffusion. This diagram shows how diffusion works in a lab. Up top, gas particles start in a crowded flask, an area of high concentration, and then drift through the open valve into the empty flask until the space is balanced. Diffusion is simply nature's automatic way of balancing out a crowded space until everything is distributed evenly. Now let's bring back our video game characters. A character's weight in the game is like what chemists call molecular mass, which is just a measure of how heavy a single molecule is. In a single room, the temperature acts like a global server setting. It dictates the energy level for everything in the area. Since they are at the same temperature, every molecule starts with the exact same amount of power. But because they all have the same amount of power, they have to use it differently. The lighter molecules don't have much weight to carry, so they turn all that power into raw speed. This is the equation for kinetic energy, which is the energy of motion. To keep the total energy on the left the same, whenever the m for mass gets smaller, the v for speed has to get much bigger to compensate. You can see this trade-off in action when comparing gases. A small, lightweight hydrogen molecule easily outpaces a larger, heavy oxygen molecule because it is converting its energy into much higher speeds. Because lighter molecules move faster on the same energy budget, they cover greater distances in less time, leading to a much higher rate of diffusion. So what happens if we want to speed up the heavy molecules? We give them a server-wide speed boost by adding heat. Temperature is a direct measure of heat energy. When you increase the temperature, you are physically pumping more kinetic energy into the molecules. With this sudden injection of energy, the molecules are forced to travel at much higher speeds. They slam into each other more violently and bounce much further apart. This is why baking bread smells so strong. The high heat of the oven supercharges the scent molecules in the dough, causing them to diffuse through your whole house much faster than they would if the dough stayed cold. Applying heat to any substance injects energy into the particles, guaranteeing a faster rate of diffusion. Let's review the final score. First, diffusion is the natural movement of particles from crowded areas to empty spaces. Second, lighter molecules spread faster than heavy ones because their lower mass allows them to reach much higher speeds. Third, higher temperatures act as a speed boost, injecting more energy into the system and accelerating the whole process. When you move from the video game world to the literal textbook, these are the core mechanics you'll find on every exam. This page shows the formal breakdown. It notes that the rate of diffusion is affected by factors like molecular weight and temperature, the exact same variables we've seen playing out in our game map. The next time you catch the scent of perfume across a room or fresh bread in the kitchen, you're seeing these laws of physics playing out in real life.